Thanks, Matthias. Let's start. All right. Peripherals provide us ubiquitous access to different functionality and have become an integral part of our daily life. Now, although the kinds and the functionality varies, these devices, the protocol used to support these devices start to converge into a couple of few, including USB, Bluetooth, and NFC. Now, recent Apple's laptops have replaced their power supply, Thunderbolt, and HDMI ports with USB Type-C ports. And we have seen the traditional 3.5mm jack audio port is merged into a single USB port on smartphones. Now, if you're not using USB, then it's likely that you're using Bluetooth, such as Bluetooth speaker, Amazon Echo, and Google Home. And you might have heard of or even used Google Pay, Apple Pay, and Samsung Pay. Now, under the hood, it is the NFC technology which supports all this wireless payment. And all we need is to connect with whatever we can find on the table and have fun. What could possibly go wrong, right? It turns out these peripherals can be malicious. Bad USB attacks allows attackers to reprogram the device firmware to add extra functionality. Now, for example, a malicious USB flash drive can type like a keyboard, injecting malicious keystrokes automatically to compromise the target operating system. Or there's a device called USB Rubber Ducky, which looks like a USB flash drive, but it is a keyboard. Now, even worse, attackers can compromise our phone by sending out AT commands from a malicious USB charging station. Now, what about wireless peripherals? Blueborn attacks allows a malicious Bluetooth device to inject worms into the target operating system by sending out specially crafted Bluetooth packet. And this vulnerability has affected 5.3 billion devices. Bad Bluetooth attacks allows a malicious Bluetooth device to change its functionality after pairing. A recent NFC 0D allows a malicious NFC device to compromise the target operating system by sending out simply malformed NFC packets. And we have seen these tapping ghost attacks, which allows a malicious NFC device to compromise our cell phones. So now we have our vulnerable host machine on the left. We have different peripherals connected on the right. They could be wireline or wireless. More importantly, they could be malicious by sending out, for example, functional but unexpected USB packets, specially crafted Bluetooth packet, or simply malformed NFC packets. So the question is, what are we going to do to defend against attacks from these malicious peripherals? Now, firewall is a pretty mature technology used by networking security. So our intuition is, let's build a firewall for peripherals, right? Problem solved, and I can close my talk. It turns out it's not easy to build a wall, either within an operating system or somewhere on the earth. It turns out there are a couple of challenges we need to fix, now, including peripheral diversity and the filtering complexity. We have seen the previous work trying to build packet layer firewalls for USB. But what about other peripherals like Bluetooth and NFC? We also need to balance between the programmability and usability. Now, for example, we're familiar with IP tables. It's friendly to use, but provides limited programmability. Another problem is how easy it is to extend the existing filtering framework if new features are needed. Now, with all the challenges in mind, we propose the Linux eBPF module, aka LBM, a generic security framework for peripherals. Now, LBM is peripheral agnostic. It can be used to instantiate a packet layer firewall for any peripheral within the kernel. To achieve that, LBM provides hooks which can be placed into different I/O subsystems instead of hacking the existing code base directly. LBM uses the extended BPF as the backend packet filtering engine. Now, BPF is an internal virtual machine designed for packet filtering. Comparing to the classic BPF, eBPF architecture as a new call instruction, allowing eBPF program to call kernel APIs via BPF helpers. We also designed a new filter domain-specific language, which supports arithmetic operation, logical comparison, and operation precedence defined by C89. Module extension is also supported. We have extended LBM to cover USB, Bluetooth, and NFC. Now, LBM hooks and eBPF help tackle the peripheral diversity issue, and the filter DSL and module extension tackle the filtering complexity. Now, this is what LBM looks like in the high level. Now, within the bottom, we have LBM hooks, which are placed into different I/O subsystems, covering both the transmission path, TX, and the receiving path, RX. The LBM core framework is structured as a generic security framework. Besides connecting with LBM hooks, it runs eBPF programs as filters. Module extensions can also be loaded into the LBM core framework. Each module then has a chance to inspect every packet from any peripherals. Within the user space, we designed a new packet filter language, which compiles into eBPF instructions by Ibmtool. Ibmtool then loads this filter into the LBM core framework. Now, hooks themselves can be complicated, and we're not the first one thinking about leveraging hooks. If you look at the classic Linux security module hooks, it has over 100 hooks across different places within the kernel. New hooks are still being added. The number and the complexity of these hooks impose challenges for verifiability. Now, compared to LSM hooks, LBM has only one, and it looks like this. The subsys parameters specify the subsystem. The dir or direction parameter specifies the filtering path is either TX or RX. The packet parameter points to the packet structure defined by this subsystem. The same hook will be placed into different I/O subsystems with different parameters. One example is the hooks we placed into the USB subsystem. To achieve complete mediation, we want to place these hooks as low as possible within a protocol stack. Now, this figure shows the USB protocol stack within the kernel. And we place the hooks next to the host controller device, which is responsible for sending and receiving every USB packet within the system. Similarly, for Bluetooth, we place LBM hooks next to the host controller interface, which is the bottom part of the Bluetooth protocol stack. Now, note that packets at the host controller interface layer follows simple TLV format, rather than exposing well-known protocol fields such as Bluetooth MAC address. Blueborn attacks also happened within the higher layer. So to make sure end users can write filtering rules using well-known protocol fields, we continue placing LBM hooks into the L2 cap layer. Now imagine you need to filter some USB packets from a suspicious USB device. You can write this filter using BPF assembly. And if you do that, it's going to look like this, with more than 20 instructions. Now with the help of our filter DSL, all you need is simple one line. And then our LBM tool takes that expression, follows the syntactic and semantic analysis to generate the abstract syntax tree. Now, based on the AST, an internal IR is also generated, which is built upon 3 address code. And finally, LBM tool emits eBPF instructions, which look like the one you have seen. Now, note that some protocol fields may require the usage of BPF helpers to retrieve their values from the kernel space. Now, nevertheless, end users do not need to know the existence of these BPF helpers. LBM2 automatically translates these protocol fields into their corresponding BPF helpers. And this filter is finally loaded via BPF syscall. Now, as a proof of concept, we'll use LBM to implement a minimum packet layer firewall for NFC and see how many lines of code we need to do that. Step 1, we need to place the LBM hooks into the bottom part of the NFC protocol stack, which is the NFC controller interface. Then we need to expose some protocol fields from the kernel space to the user space. Now here we write a BPF helper to expose the message type of an NFC packet. Step 3, we need to extend LBM tool to recognize this new protocol and its corresponding protocol fields. Now here we add support for packet length and message type. That's it. And then users can write simple rules like this to drop NFC packets. The total number of changes is within 100 lines. To test the ability of LBM to defend against malformed packets, we use FaceDancer, which is a USB hardware fuzzer. Now, after connecting FaceDancer with the target, we're able to send out malformed USB packets to the target. To defend against exploitations from malformed packets, we can write a filter to drop these packets before they hit the protocol stack. Now here we write a filter to drop malformed packets during the USB enumeration. What we are doing here is to check all the USB protocol fields within the packet, making sure that all the values are within the range defined by the USB specification and that the packet itself has a minimum length of payload. Now, after plugging this filter into LBM, we're able to defend against from the FaceDancer. We also implement a similar protocol stack protection for the Bluetooth HCI layer. To defend the classic HID-based bad USB attacks, we can write a filter to allow only the trusted input device to inject keystrokes within our system. Now, this filter says only my keyboard can type within the machine. Or even better, we can write a filter to turn certain physical USB ports into charging-only mode by dropping any USB traffic. Now, this filter is particularly useful if you need to charge your laptop in a public charging station, or someone asks to charge her phone on your laptop. Now recall that blue-born attacks allows a malicious device to exploit a kernel stack overflow by sending out a specially crafted Bluetooth packet. To defend against the blue-born attacks, all we need is to drop that offending L2 cap configuration response packet with length beyond 66 bytes. Now, after our paper was accepted, bleeding beat attacks were also disclosed. There were similar attacks like blue-born, but targeting BLE stack. By disabling BLE connections using this filter, we provide a temporary workaround to defend against bleeding beat attacks while maintaining the classic Bluetooth connections. Now, note that both blue-born and bleeding beat are vulnerabilities within the Bluetooth software stack. And LBM provides us a way to dynamically patch the kernel without waiting for kernel patching and rebuilding. To understand the overhead introduced by LBM, we use FileBench to measure the overhead of I/O operations on an external USB 3.0 hard disk with mean file size 128 kilobyte and 1 megabyte, which roughly generate 1 gig and 10 gig workload. We compare among different kernel configurations, including the stock kernel, the LBM kernel, and LBM JIT kernel, which enables just-in-time compilation for eBPF instructions. Now, regardless of the mean file size, both LBM and LBM JIT have demonstrated a minimum overhead compared to the stock kernel. And in the worst case, the overhead is still less than 1.8%. To understand the scalability of LBM filters, we load 1, 10, and 100 filters into LBM and measure the overhead of receiving 10K packets using a USB Wi-Fi adapter. Now, the general overhead increases as the number of filters increases, and LBM JIT has better performance than LBM thanks to the acceleration from JIT. Nevertheless, in the worst case, per packet per filter filtering is still within 1 microsecond. Now, as other security frameworks within the kernel, LBM is not perfect. Right now, LBM does not allow BPF memory writes for security considerations. Now, in the future, we probably will enable that, allowing modifying the packet in the fly. For example, redirecting suspicious packets into a honeypot. Unlike other BPF programs, LBM does not support LVM. We argue that our filter DSL is more friendly than typical C programming. The LBM filters are essentially stateless. However, BPF maps can be used to store this stateful information. For example, counting how many packets we have received so far. And some filters can also have protocol fields which are essentially stateful. For example, L2 cap connection field. Now, LBM supports USB, Bluetooth, and NFC. But what about other protocols such as HDMI, DisplayPort, and even Thunderbolt? Now, in theory, as long as a protocol has the conceptualization of packet, LBM is able to support it. Now, both HDMI and DisplayPort have the concept of packet. We're not sure about Thunderbolt because it's proprietary and closed source at this moment. So in conclusion, we design and implement LBM, a generic security framework for peripherals. We have extended LBM to cover USB, Bluetooth, and NFC, And our evaluation shows its effectiveness against different attacks from malicious peripherals and the minimum overhead compared to the stock kernel. Thank you. I'm able to take questions now.
Okay, questions?
Peter Neumann, SRI. Your original title was withheld for responsible disclosure. You didn't talk about that at all in the talk at all. The title in the program seems to be the wrong title. So I'm a little interested in what's really going on here from the point of view of the responsible disclosure. The other comment is, have you looked at our thunderclap paper at all from NDSS?
All right, so there are two questions. The first question is because one of our funding source required us to submit this paper before disclosure, and somehow like we screwed a little bit. So we're still working on it. So that is the disclosure thing. Second question. Yes, so LBM is not designed for defending against DMA attacks, because I assume we probably need IOMMU. Although I think Thunderclap paper tells that there could be something wrong within MMU, especially on the configuration side. But in general, I think to defend against DMA attacks, IOMMU is the basic unit, and we probably can build something upon that. Thank you.
Hi, I'm Paul Kotcher. I'm independent. Super interesting work. I had a question, which is, have you thought about what the most malicious things somebody can do with LBM scripts, and particularly in the cases where they're being submitted from user mode? Thank you.
Okay, cool. I haven't thought about that because in our threat model, the whole kernel is trusted, and apparently you need root permission to submit some eBPF programs from the user space to the kernel space. So if the user is malicious, yeah, basically he could do a lot of stuff. So I haven't thought about that. Really good question. Thank you.
Hi, Alex Olenek from Boston University. One of the things you showed is filtering based on the product ID and the vendor ID. Have you thought about how difficult it would be for an attacker who knows that you have these filters installed on the system to modify their attack in order to bypass your rules, for example, by spoofing the IDs?
Yeah, this is a really good question. So apparently attackers can reprogram the firmware to bypass these like vendor ID, PID based checking. That's the reason why within the USB filter, we also have another field called plugin time, which is used to defend against these kind of attacks. And in the worst case, you could leverage the physical USB port information to build your filtering rules, saying that anything plugged into this USB port have to be non-keyboard or something like that. But yes, attackers can reprogram the firmware to bypass some of the rules. It always depends on how you construct these rules to defend against these attacks.
Thank you.
Thank you.
I also have a question, actually.
Sure.
So I wondered, USB and Bluetooth and all these other protocols are massively complex, and they have a massive amount of state. You mentioned state a little bit, and you mentioned in one of the slides with the Bluetooth stack overview that you had hooks at different levels of the stack.
Yeah.
Right. Did you look at the complexity of these protocols and what you could do to make this easier to manage or handle, because there will be limitations in the system about?
Yeah. I mean, fairly speaking, compared to Bluetooth, USB is kind of like reasonable. Bluetooth is super crazy. If you look at Bluetooth 5.0 spec, it has almost 3,000 pages. That does not include all those high-level application layers. If we take Bluetooth as an example, our original design plan was to put these hooks as low as possible. But then we realized end users are not familiar with those like fields within this layer. That's the reason why we try to place hooks in the higher level layers. But again, if some attacks happens even within higher layers, such as SDP or some other things, which means either we need to pass the application level protocol at the lower layers, or we need to place hooks into the higher layers. So I think that could be a trade-off here.
And for USB, you focused mostly on the USB core, on just the messaging signaling, or did you also look at individual drivers and protocols that were running on top?
We are focusing on USB core.
Okay, cool. Any other questions? Okay, let's thank the
Thank you.
speaker again. Awesome.